Hello, good evening, everyone. So, so let's wait 2 more minutes so others can join, and then we will start. Am I audible? Right? Hello. Can anyone confirm that am I
Yeah,
audible
we
or
can
not?
hear you.
Yeah. Thank you. Hello. Once again, good evening, everyone. So, before we start today's content, so anyone have any doubt in week 1 to 4? Hello. If you have any doubts in week 1 to week 4, then you can ask.
So the level of difficulty in the quiz will be same as in the mock.
Yes, yes, you can expect also. So everything will be from the slide or whatever we have discussed in the live session. That's-
Hmm.
Other than that, any question?
Sir, I have a question from the tutorial of week 6.
Yes. So today, week 6, we are going to discuss about this session. So if you have any doubts since the week 1 to week 4,
Uh, can you explain this concept of the candidate key, primary key, super key, and those? How do
yeah,
you identify which are those three, four different kinds of keys, right?
okay.
So that concept is not very clear as to what do we start first and how do we arrive at, say, primary key or super key or
Okay, okay,
candidate key.
okay, right. Okay, let me share my screen.
So if you can put it in a very simple layman terms, it'll
Yeah,
help.
sure.
Also, say some rules probably on how to go about checking it. That would be good.
Correct.
Okay. Is it visible? My screen.
Yes.
Sir, one small dot. Can you go to the practice assignment week 2?
Okay.
There is a questions in which the how many primary kid. Sorry. Wait, I think there is a question. Question number 2. Practice assignment 2. Question number 2. How many? What is the maximum number of possible super key?
Okay. Just.
So I think we are covering the same question, right? I mean,
Yeah.
same
Yes,
topic.
yes. That's why.
Yeah.
Uh,
Okay. So this is from week 2, and which activity?
practice assignment question number 2.
Discussion. Okay. So yeah. So let me take this screenshot. Okay. Okay. Is it visible, right?
Yes, sir.
Yeah. So first, let me discuss what is candidate key, what is super key, and what is primary key, right? So first one is candidate key, primary key, and a super key, right? So super key is any set of attribute. Suppose you have a relation R with A, B, C, D. So these are set of attributes. This is your tables, and these are the set of attribute. Means these are the column value of a tables, right? So what super key means, if any set of attribute or a set of attribute can define each table value, each tuple value uniquely. So what I means, so let me take the value of this one. So suppose this is A1, B1, C1, and D1, and this is also A2, B2, C2, D2, B3, B3, C3, and D3. So what candidate key means, suppose this I took this particular attribute A. So can you tell me if I choose this A is able to identify each tuple uniquely or not? So you can tell me. So here you can see, if I took this tuple as the A1, if I search for A1 can tell me, so this is the unique tuple, right? It is like name or your Aadhaar card, right? So if I choose the Aadhaar card as the super key, so I can tell what is your name, what is your address, right? Is it? So yeah, that is a practical example. So this Aadhaar, name, and address, right? So if I took this one, Aadhaar, then I can tell, so what is your name and the address also. So this is, you can call this is a super key, right? Aadhaar is your super key because Aadhaar is able to identify the each tuple or each value in a row. So suppose this is A1 is a one tuples, one Aadhaar numbers of name of a person is N1 and the address is this one, right? And the A2 also like this one. So what super key means? So this is Aadhaar is your one super key, right? So whatever attribute you can add to a super key, this key, that is also a super key. So you can, that means Aadhaar, or you can add the name also. So Aadhaar or name is also unique, right? So that can identify each person also. Similar way, whatever you can add, address also. So that is always unique. It's like if 1, 2, 3 is unique value, your whatever you can add to that value. Suppose you want to add 2, 2, 2. So these all are unique value, right? So that is called key, or so this is called the key. So key means that should identify each tuple uniquely. Key is clear, right? Key and the super key also. So all these are called the key. And right, and super key is similar to that. So this is one super key. And what is the candidate key? Candidate key is any proper subset of a super key that should that can identify each tuple uniquely, right? So this is your super key, right? So this, suppose this is this you got, these are the super key: Aadhaar card, Aadhaar and name, and Aadhaar and address, right? These are your super key. So can you tell, so this is your uh, uh, candidate key or not? Anyone?
So which one, sir? The only other.
Aadhaar and name. So this is one your super key. So this is super key 1, this is your super key 2, this is your super key 3, right? So can you tell me this super key is your candidate, also your candidate key or not?
I think
That is
SK1
also,
is, but
yeah.
not SK2 or SK3.
Yeah, that is exactly difference between super key and the candidate key. So all the candidate key are also super key, right? All the candidate key are super key, right? So if we took any proper subset of the super key, right, that should if any proper subset of a candidate key can identify each tuple uniquely, then that is not a candidate key. That is, you can call that is a super key, right? So what is the proper subset of this super key? Not possible, right? This is only one attribute, right? So here it is possible. So Aadhaar card is one proper subset of this super key. One is Aadhaar, and another is name, right? So you have to check whether Aadhaar is a super key or not, and this is a super key or not. So here you can see Aadhaar is also a super key, right? So this is not a candidate key. S2 is not a candidate key, but this S1 is a candidate key. You can.
So in other words, we can always find a subset of either SK2 or SK3 which can uniquely define the tuple, right? Because in this case, if Aadhaar is the
Yeah. Here
subset,
it
right?
is possible, but every
Right,
situation not. It may be not possible.
right.
Yeah. So that if I give an example, then it will be all clear. Okay. Let me give another example.
So for basically for super key, we have to to actually try every permutation combination of the
Yeah,
given
first
relation.
you have to find the candidate key, then you can add if you find. Okay. So suppose this is your table A, B, C, D, right? So if your candidate key is given, so A, B together is your candidate key, right? Together. This parenthesis means together can identify each tuple uniquely. So this is given A, B are candidate key. So can you tell me what are the super key possible here?
All combinations with AB, sir? Is that?
Yes. So
It will be
A,
like
B,
A, B, and C, and A, B, and D, right?
no. A, B
And
must
ABCD
be
also.
there.
Even
A, B,
ABCD also. Right?
A, B, C, A, B, D,
Yeah.
And A, B, C, D.
and A, B, C, D. Right, these are only possible, right?
These are super keys.
Yeah, these are super keys. And from this, only this is candidate key.
And sir, what is the significance of AB? What did you say at the beginning?
So this is given to you.
Okay,
AB
that is
is, yeah. So that means here you can see the parenthesis is given. So all three attribute together is one candidate key. So these are not different.
So in the math we studied power set. So that means once we
Yeah,
know the element, right?
that is
So
exactly power set.
right?
So this is, you can think like this is empty set, this is one set, and this is one set. So exactly we are using that formula only to find the candidate.
sir. Whether the sequence also matters?
No,
Sequence means
no.
sequence doesn't matter. Like if I write DA or
Yeah, you
DBC,
can write.
that means the same, right?
Yeah. So what is the formula how to find the super key here? So you can simply, so A, B are your candidate key, right? So that is, what is the 2 to the power, right? What is the numbers of remaining attribute, right? That is numbers of remaining attributes. So that is your 2 to the power 2, right? That is your 4. Exactly, here you can see this is your numbers of super key.
I think it's like math 1 days or stats 1 days.
Yeah. It is set theory. So
Yeah.
you,
So
Can
number of
you just
elements in
repeat
the
that?
power set
Number
is
is
2 to the
numbers of super keys, possible numbers of super keys. So this
I
is the
mean,
maximum.
mathematically, how did you get it?
So you know about the power set, right? So if this is, so these are your, suppose this is your set value, right? This is set. What is the, can you tell me what is the possible numbers of set in that power set of value? So that is,
2 to the power 4, na? 4 elements are there.
that is 2 to the power 4, right?
Right.
So this is clear to you, right? Power set. Okay.
So if the number of element is small n in the original set, then the power set will be 2 to the power n. Because if you add the sum of binomial number, I mean whatever that I think.
Yeah. Then you have to check what are the permutation combination, and you also here you have to check the union also.
Yes.
Union. Yeah.
Sir, but here a fundamental doubt is coming to mind. Like you are saying that AB should be there, right? So when I will write all the sets in the power set, then AB will not have occur, in all the elements. Like even A will be there, B will be there, C will be there, D will be
No.
there, empty
I
set.
ignoring that part. So
Okay.
this is the permanent. Permanent. You can say this is always be there. So that's why I minus that one.
Okay. So total
So the way
total
we
elements will be
remember,
16. Total
Yeah.
elements will be 16 since 4 elements are there. So number of elements in the power set will be 2 to the power 4, 16 elements. But out of them, only some will be super key, right?
That is the numbers of remaining attribute. remaining attribute means those are not candidate key.
No, first of all, we'll start with super key, na? Super key, then candidate key, then primary key, na?
No, you have to first find the candidate key, then you try to find the numbers of possible
Okay.
super keys. So you can reverse is not possible. Only you can find the numbers of possible from the candidate key. You can find the numbers of possible super keys. Right.
So here in candidate key, there are only two elements, A and B, right?
Yeah.
So what will be the total number of super key then?
Then the possible numbers of
2
super
to the
key
power
is
2.
so A. B, yeah. A B
Right.
is always be there, right? Okay. Then what it will come? So first element is your empty set, right? So you have to consider only the remaining attribute. So what is the remaining attributes? Numbers of remaining attribute, that is C and D, right? Then your second is A, B, then A one possible, not A,
C.
C is possible,
Yes.
right? Then A, B,
D is possible.
then D is possible, and 4 A, B, and C, D is possible.
Right. So these 4 will be super keys.
Yeah, this 4 is super.
So while writing in separate sets, sir, ABCD will be in the same set. Na?
So I make you to understand that.
Okay. Yes.
So it's almost like a restriction, right? So if
Yeah,
AB is the candidate key,
this,
my
this will be
element is now
always there.
CD.
This will be always there,
Yeah.
right?
Yeah.
Okay. Up to this is clear how this formula is can.
Yeah.
Okay. So now move to this particular question. Okay. So here you can see question is consider the following relational schema of the student of a school. Okay, student information. These are the set of attribute 1, 2, 3, 4, 5. There is a total numbers of attribute is 5, and these okay the enrollment number and the class section and roll numbers. These are the two candidate keys is there. So you have one candidate key, that is enrollment number. Okay. And your second one is right. So using this particular candidate key, can you tell me how many numbers of possible super keys? Numbers of possible super keys. So that is exactly the same. So here you can see 2 to the power numbers of remaining attribute, right? Only one attribute in your this candidate key, right? So what is your remaining attributes? That is 5 minus 1, right? So that is 2 to the power 4. Okay, so that is your 16. Using this particular candidate, this is the numbers of possible super key, and using this as super key candidate key, okay, this one. So here 3 attribute, right? So what is the numbers of possible super key?
To the power 5 minus 3.
Exactly. So that is 2 to the power 5 minus 3. That is your 2 to the power 2 equal to 4. So here one catch is here. So here you can see there is a repetition. So every combination of using this particular as a candidate when you consider this one, enrollment number and combination and roll number, right? Three attribute. This combination you have count using this as a candidate key, or if any super key has this attribute, you include here also and here also, right? Count here also and here also. In this count also, right? Here also this combination is there, you have count, and so I means you have count it twice, this combination of the super keys, right? So you have to subtract that also from this total numbers of this combination. So
So
you
we
have
have to, so we
you
have to
have
take
to
intersection
yeah,
between these two.
so you have to find yes,
So do you have to take intersection between these two and
yeah,
then?
yeah, yeah,
Yeah.
yeah.
Okay.
So that is exactly intersection. So you have to subtract that also. So that is your 2 to the power 5 minus remaining attributes, that is 4, 2. So you have to simply union. So how we sum up the union, these attributes,
So how did you get the 2 to the power 5 minus intersection?
So this combination here you can see enrollment number, class,
So there is
section.
only one remaining, is it, sir?
Yes, yes.
Okay, okay, okay.
5 minus 4. That is,
Okay, yeah, got it, sir.
yeah. So that is exactly 20. That is 18. I hope it is clear to everyone.
Yeah. So if we say this first candidate set, whatever that set containing three element on the top, that's
Yes.
set A and this is set B, then I think A intersection B is this
Yeah,
formula,
yeah,
right?
yeah.
Cardinality,
Yeah.
right? So that's
Yeah.
what it is, right? The set theory.
Yeah.
A plus B minus A intersection B,
Yeah.
right? To get the
You
A.
can think this question like as more set theory question.
Right, right.
Okay. It is clear to everyone, right? What is candidate key and what is super key and what is primary key? That is also clear.
So from this, how will you determine the primary key? I mean,
Yeah,
you've got your
primary-
candidate key, you've got your super keys, right?
Yeah. So
So
there is two possible of candidate key, right? So you have two options to choose the primary key, right? So it is up to you, whichever you want to choose. So in a tables, in this table, so in this table, student info, there is two candidate key. It's up to your uses. You can determine whichever the primary key. So suppose you consider the enrollment as the primary key. So then enrollment number is your primary key. So primary is one of the candidate key. Right. So if you have decides the enrollment numbers as the primary key, right, then all other than this primary key, these are called the alternate key. So if you decide this as the primary key, then you can say this enrollment number is your alternate key. So that is alternate key.
So primary attributes are two different things, right, sir?
You are not audible. Can you repeat?
So primary key and prime attributes, they are two different things, right, sir?
Yes, true, different.
Okay.
This is clear, right? What is super key, what is candidate key, what is primary key, what is alternate key? Yes or no? Hello?
so basically, the order of hierarchy is first all the super keys. From super keys, you identify candidate keys, and
No.
from
No, first I identifies the in a tables, how you can identify that. So in a tables, first you have to identify which are the candidate key, right? So you have to
okay, so
identify the
for that,
candidate.
okay, so someone has to specify these are the possible candidate keys, like the
Yeah, it
business
is
person.
already given to you. That's why no need to find how to can finds the candidate key, right?
Okay.
So first you have to find the candidate key. Then if the question is like you have to find the maximum possible numbers of super keys. So you can add two attributes in the candidate key and you will find the super key, right? Okay, let me give an example of that one. I hope that will be
So
clear.
basically, super key is a combination of all the attributes along with the candidate key.
Yes. So suppose this is your one example. So I hope all you know how to find the
But there
candidate
was
key.
some statement, right? All candidate keys may not be cannot be the primary key.
Yes. So yeah, previously I was tells that this one of the possible, if there is a, suppose there is a four numbers of the candidate keys, right? A, B, C, D, right?
Okay.
These are your candidate key, right? So you can say A is also one of your candidate key, B is also one of your candidate key, and T is one of your candidate key. Suppose you are a database administrator and you want to choose one primary key because only one is possible as the primary key, right? So suppose you as a database administrator, so you choose B as your primary key, right?
Okay.
Right, you choose B as your primary key, then A is not possible to be primary key right now. During this, only one is possible at a time, at a one time. Maybe some other few week later you decide A should be the primary key, then you have to drop this as a primary key, right? Then you can assign A as a primary key. At a time only one is possible as a primary key, right?
Okay.
Okay.
Uh,
So this, yes.
Pradeep sir, here I have a doubt, sir. Like I think primary key has further constraint, right? Like primary key cannot be null or it cannot be
Yeah,
repeated,
that
right?
is also the candidate key also same
No,
constraint
no.
is used.
So my point is that whether all the constraints are applicable for candidate key also.
Yes. So
So
these,
can we say that all the primary keys are candidate keys?
yes.
And similarly all the candidate, okay, so
No, all the candidate keys,
no, no,
reverse is not possible.
though we are going to select only one, but all of them have potential to be a primary key, right?
Yes.
But then what is the difference between the candidate key and alternate key? Because all the keys which have not been selected as primary key are known as
Then
candidate key, right?
yeah. So
So
this is,
then what is the difference between candidate key and alternate key?
yeah. At this particular instance, B is your primary key. Then A, C, D
Alternate
is
key
your
as well as
alternate key.
candidate key, right? So what you are saying that those two
Yes.
constraints are equally applicable for candidate key also, that it should not be null and it should not be repeated, right? But then why the
Yes.
converse is not true? Then we can say na, that all primary keys are candidate key also.
Yeah, all the primary key are candidate key, but all the candidate key are not primary
Why?
key.
When all the conditions are getting satisfied, then why converse is not true, sir?
So that is the definition of the primary key, right? So primary key in a database, only one primary key is possible, right? Okay.
I think if you refer to the lectures by Professor,
right.
I think the example they were talking about Aadhaar and then passport, and you'll see that there are two things, but sometimes depending on the context, one is chosen, and the one that misses out basically becomes alternate key.
No,
So
no. In that lecture now, why professor had not choose Aadhaar number, because it may happen that some people are not having Aadhaar number. So he said that the condition that it should not be null is getting violated here. So we are not choosing Aadhaar
actually, that was
number.
for passport, Ganga. That was for passport. For
Anyhow, okay,
Aadhaar,
let us
yeah,
take passport itself. So passport was not chosen as a primary key. So that was
right.
my reason why I'm asking whether those two conditions are equally applicable for candidate key also. Because for primary key, these two are primary in very important conditions, very critical
Okay.
conditions.
So in that condition, the passport may be null,
Yes.
right? Then that is not a candidate key.
Okay,
Candidate
that
key,
is not
yes,
candidate
correct.
key also, right?
Yes.
Right. And if we choose that lecture, like so, both Aadhaar as well as the the enrollment number are candidate keys, but why that roll number was selected is because it contained more information, right? That was 16-CS. So by looking at that key, it gave us a lot more information compared to Aadhaar. So in that context of university application, that enrollment number as a key actually was a lot more useful because that gave lot more information that is applicable for that context. So that's why that one and Aadhaar was basically not selected, so it basically becomes alternate
I
key.
agree with
So
you.
sometimes it's not a
Devasis, I agree with you, but
yeah. Sorry,
as
go
per
ahead.
Devasis, I agree with you, but as per conditions, when we are saying that all candidate keys are having equal potential to become a primary key, right? So
Yes.
why converse is not true? Why all primary keys are
So,
not?
actually, one table can have only one primary key. Okay,
That's
so
fine, but others have
yeah,
potential, na?
that's why those are other are potential, but those are called as only candidate keys then, or alternate keys.
Maybe the way to
Every
put
table
it
is
is
having only one primary key, primarily because I think when you set something as a primary key, your actually data gets sorted by that.
Right.
That's called as an index.
Yes.
Okay, so it is not possible to get index data every now and then. So every table has only one primary key, and remaining candidate keys are called as alternate keys.
so maybe the way to put it is, let's say the candidate keys are the finalists. Let's say we have a race, right? So all these attributes can become candidate, but only a subset becomes the finalist, right? In the final, only there can be one winner. The winner is primary key. Everybody who lost the finals basically are alternate keys. So essentially, it's a kind of, and these two sets together define our candidate key.
So what?
Maybe that's the better way to kind of
So what is the
think
final
about this.
statement? All candidate keys are primary key.
Right? Because to win, you have to be in the finalist, right?
Yeah, that is a good example. You can understand like this. Suppose there is one, so these are competitor. You can think like this. Only in first, only one seat is possible, right? One, but in the second position, all other, not in the first position, then are come in the second position, right? So that are called alternate, right? This position is called the alternate, right? And you can think like this is the primary key. So at a time, only one is possible as the one primary key. Suppose B is in the primary key, then A, C, D is on the alternate key, right?
So what is the final statement, sir? All primary keys are candidate key, but converse is not true.
Can you say it again?
What is the final statement?
Okay.
All the primary keys are
All
candidate.
the primary key are candidate key, but reverse is not true.
Okay, but reverse is not true, right?
Yeah.
Okay.
Yeah, all winners are
Correct.
finalists are in the
Yes.
final, but
Yes.
all finalists are not winners,
Not
right?
winners. Yes. Correct.
Yeah.
Okay.
Also, the primary key could be a combination as well, right? I mean, if suppose there are no single attributes that I get as a candidate key, then a combination would be a primary key, right, sir?
Yes. So here you can see there is two possible, right? Enrollment numbers and the class section and the roll numbers, right? There is two candidate. You can either choose this one or this one.
So the second one would be a combination, right? It's a class.
Yes,
number.
yes, combination.
Yes, sir,
I
it
hope
is.
it is clear.
Thank you.
So many times the database, the combination, a lot of bunch of foreign keys will define the as a primary key. If you are like a transaction table, whatever,
Yes.
right? It's drawing from different tables. So that's a very, very frequently occurring phenomenon.
So someone has asked some question. So how to find the candidate key? What is the so you know how to find the candidate key here, right? So suppose this functional dependency is given to you, A to B one functional dependency and second one is a B to C, right? So you can find the functional dependency. How you find? So suppose this relation has three attribute, right? So you have to find the candidate key. How you can find the candidate key? So you have to check the left. First you have to check the right hand side. So here you can see right hand side B is present, right? C is also present, right? So only A must be in the candidate key. must be as attribute in a candidate key, right? So you have to first check this combination, either it is possible or not. So if this is closer set of attribute of A, you have to find. So can anyone tell me that what is the possible A to A, right? Please, anyone?
AB, and then ABC.
And then ABC.
Yeah.
That is equal to R, right?
Yeah.
Okay. So this is whatever, this is your candidate key, right? Only one candidate key here. A is your candidate key. Any other candidate key possible here?
Not here, given the FD. If we change the FD, maybe.
Yeah, you can. If I change the FD, then yeah. So here you can see you find the candidate key here. Then if I ask you what is the possible numbers of super key here in this relation, right? So can you tell me what is the possible numbers of the super key?
I think 2 to the power 3 minus 1.
Yeah, that is 2 to the power 3 minus 1. That is 2 to the 4 is possible. So this is like this only. Okay, so one concept is here also. So this is your candidate key is A, and right, you find the candidate key A. So I want to introduce two terms, that is prime attribute, and the second one is a non-prime attribute. So prime attribute is that attribute that is present in the candidate key, right? That is called the prime attribute. And non-prime attribute, the attribute that is not present in the candidate key. So in this example, can you tell me which attribute is your prime attribute and which attribute are non-prime attribute?
A is prime and others are.
A is prime attribute and B and C is your non-prime attribute, right? So that attribute that is present in the candidate key, and so non-prime attribute that is not present in the candidate key, right? So in this
Excuse me,
example,
sir.
yes.
Sir, I have a very small doubt. Sir, if there are only three attributes total here in this relation, then how can be like four super keys? I'm lost. Like,
Where here?
yes, sir. In R, A, B, we have three
Okay.
attributes A, B, and C,
So
and
yeah,
possible super keys are four.
okay. So A is your candidate key, right?
Yes, sir.
Okay. So A is one super key possible, right?
Yes, sir.
Second is possible your AB possible,
Yes, sir.
right? Third, AC is possible,
And then A, B, C. Okay, I got it.
and,
Sir.
and
Thank you.
AC is possible. And this is your formula, 2
Yes.
to the power numbers of remaining attribute.
Okay, sir.
Okay. So continue to this one, prime attribute and non-prime attribute. So can you tell me here what whichever attribute are the prime attributes and which are not non-prime attribute?
That the attributes which are part of candidate key are prime attributes.
Okay. So can you tell me here prime attribute are in this example?
In this example,
Candidate key is given, right? This is your two candidate key. One is enrollment and so
The
prime
enrollment
attribute.
number,
So
class, section, and roll number.
okay. So this is your prime attribute. This is also your prime attribute. This and these are the prime attribute, right? Enrollment. Enroll. This is your prime attribute, and non-prime attribute are only name is non-prime attribute because that is not present in the candidate key, right? So you can, name is your non-prime attribute. So prime, non-prime is clear to everyone, right? So this thing is we are going to discuss since the normalization, prime attribute or non-prime attribute. Okay, hope it is clear to everyone. So prime attribute, non-prime attribute. Okay, continue to this. It is visible, right? Normalization is.
Yes, sir.
Okay, thank you. So yeah, so first we see the slide. What is in the slide? So in the before moving to that, any doubt? Anyone have any doubt? Whatever we have discussed.
I think one quiz question is definitely guaranteed now.
Okay, no. Okay, fine. So we will see the normalization, right? So normalization is the first we see the definition. So normalization or the schema refinement is a technique of organizing the data in the database, right? So what we see, we generally define a relation in a database, and we identify the attribute, right? So maybe possible because of you identify the relation, maybe possible you all together the you store all the information at one tables. Maybe possible, suppose like this, all the university data are you create one tables in a university table, right? And you store all that, you defines the all the attribute for the faculty and the all the for the student, and you create one tables, and you all the information you have inserted on this in that tables, right? So maybe possible that's the redundant information, you maybe repeated some information, right? For the student, if you assign some course, so maybe every times the course and the course detail also maybe repeat with it. So that should be resolved by the normalization, right? So that is the goal of normalization, element redundancy. So redundancy means repetition of the data. So we inside DBMS, we trying to reduce that redundancy so that we can keep the data organized into different information in different tables, right? Like the faculty. So we defines the faculty tables. It will contains all the information related to faculty, all the student tables, right? Generally we do it for the for ins the relational algebra, right? So yeah, so normalization is a systematic techniques to redundancy, that data redundancy or undesirable characteristic. So what are the undesirable characteristic? That are the insertion anomaly, update anomaly, and the deletion anomaly. So because of the data present in one tables, these all are maybe possible, these undesirable characteristics. So we will discuss about one by one, what is insertion anomaly, what is update anomaly, and what is deletion anomaly, right? So we will discuss one by one. So first we will discuss about the update anomaly, right? So first, let me define what is this table. So this table is the supply tables. This is your supply tables. This is your SID, supplier ID, and this is your status of your city, and this is the city from which the supplier belongs. And PID is your parts ID, or you can simply say also the product ID, right? And this is your quantity. Okay, so here it is given SID and PID your key. So, So this is your SID and this is your PID. This together is your primary key. Key means primary key here. Right. So here you can see what is update anomaly. So for the S1 supplier ID, right, SID S1, you can see Delhi, 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 right. Maybe possible this S1 is moved from Delhi to Chennai, right? Maybe possible. So you have to change also the supplier city also here. So suppose every time you change the tuples one by one, suppose this you have changed Chennai, this also you have Chennai, and this also changed Chennai, but you have forgot this to change this one. Now, if I ask you what is the city of the supplier ID S1, then there is redundant. You cannot tell the whichever the city because two cities was here, Chennai and Delhi. So because of this repetition of the data, so one possible this update anomaly may be possible. So this concept is called the update anomaly, right? And okay, update anomaly is clear to everyone, right?
Yeah. And typically the process will fail because of hardware failure or power failure, stuff like that.
No, no. This is we are not talking about. We are just discussing about the concept. Maybe
Right.
possibly you update one by one, one tuple at a time.
Right.
Suppose you have changed here or here also, but you forgot to change here also.
Got it. Got it.
So this is your update anomaly. And what is your insert anomaly? Suppose you have hired one new got new supplier ID, right? That is S5. S5 with city. Let's take it Chennai. And the your city status is 45, right? But here you cannot insert that value, right? Because you needs the PID also, because PID is your primary key. So for insert any supplier ID, a new supplier, you have to, that supplier ID have to supply at least one product, right? To insert. This point is clear, right? To insert that supplier, new supplier ID, that supplier ID at least supply one product, right? So that is called the insert anomaly. Is it clear? You cannot insert this value, right, here in this tables because he not supplied any product I. So that's why. So that is insert anomaly. And what is deletion anomaly? So deletion anomaly, here you can see S3, right? S3 for Rohtak, supplier ID S3 and the status 40 and the Rohtak. So this is only one instance of this supplier ID, right? So suppose if you want to delete this product ID, right? It got deleted the whole tuple, right? So if you want to delete this product ID, right? This product ID means I want to delete this tuple. So here you can see you lost the information of this supplier ID also because of this. If you want to delete this PID, this tuple. Got it? What is this delete anomaly? Right? Because you want to delete some other information, you lost another information that is required to you. So that is your update anomaly, that is insert and the delete anomaly. Clear? Anyone have any doubt to this part? No. So we can proceed to the next one. So these are the two desirable properties of the decomposition. So because of that redundancy, we can solve that. We do the normalization. So to do the normalization, we decompose the tables, right? So that is a decomposition is, if I explain in a very high level, so you can see this is the tables. If this table has the redundant data, then we can decompose, right? R1 and R2. If this table have any other redundant information also, then you can decompose into further, right? R13 and R14. So that is the decomposition. So what happens when we decomposed the information, right, into R1 and R2? We need to take care of this one. So the decomposition need to be lossless joint decomposition. So what that means, suppose if a relation R you decomposed into R1 and R2, maybe in the later stage you have to extract the information, that is by combining these two tables, right? Or you can reconstruct the tables to extract some information or retrieve some information, right? So that should not be contains any more tuple or less tuples than the original tables. So what exactly that means? So suppose this original tables has the 50 tuples, right? And you decomposed it into R1 and R2. And if you try to reconstruct it, right? And if you got 100 tuples or maybe possible so 20 tuples, right? So then this is your lossy decomposition, right? So you lost the original information, whatever present previously, right? Clear? It is clear.
So only thing is the at each level the functional dependency has to be given, right? So when we go from R to R1 R2,
Yeah,
certain
yeah.
set of FD has to be given. Then when we split R1 to let's say 1 3 and 1 4, then the FD below will be a subset of above, right?
Yeah, yeah.
Yeah. Okay.
Okay. So this is your first point. So the table should be lossless joint decomposition. And the second one is your dependency preserving. Dependency preserving means, suppose this table has this functional dependency. Suppose this table has your functional dependency this, and you decomposed into R1 and R2, right? Okay. So if this functional dependency F1 and you have got F1 and F2. So F1 functional dependency associate with R1, and F2 is a functional dependency associate with R2. So whenever you reconstruct to want to reconstruct to the original relation, so you have to also get the original functional dependency also. So you can think like this as, if F plus means this is a closure, right? So these should be proper subset of F1 union F2, then is this close. This is clear. This one should be this F1 union. So if
So
I
could you explain the F plus and this with an example? Is that possible, sir?
yes, yes. Okay. So suppose this is your R with A, B, C, and this is your original functional dependency F with A to B, right? And B to C and C to A, right? And you decompose this relation into, don't go with why we decompose like this and that. So just simply assume you decompose this as AB, right? And this one as to BC, right? So maybe whatever you have to find then which are the associate functional dependency with this one, right? So functional dependency, you have to find the closer set of this. So you can See, this is the functional dependency associated with this R1, right? And
So
again,
basically, F1 you would always pick from the main.
yes,
This.
yeah. We
Okay.
always derive from main
Okay.
this main functional dependency, and whenever we try to, so let me complete this one, A to B, and here this one is B to C and C to A. This is your F2, right? This is your functional dependency F1 associate with R1, and this one is R2 BC associate
Pradeep,
this. Yes.
C to B, F to C to
Oh,
B.
yeah. Okay, sorry. So that is C to B. Okay. So these are the functional dependency associated with it. So when you got this table and this table, if I want to reconstruct it to original tables, so I should get all the functional dependency of it, right? So here you can see if I try to get the original functional dependency. So what all my functional dependency F1 union F2 closure. So that are the possible set of functional dependency A to B, B to A, B to C, and C to A. And here also you can see A to B and B to C. Then I can say by the transitive property A to C is also possible, right? B to C is also possible, C to B is also possible, but there is a lot of possibility. But here you can see this functional dependency it has, yes it has, and the B to C is also present here, and C to A is also present. So that's why I wrote this one. So F should be the proper subset, proper or the set of F1 union F. This one.
So when you say F plus the closure of F, does it mean all the functional dependencies that are there in F?
Yes,
Does
that
it
should
mean
cover.
that? Okay. And does it include like A to B, B to C, C to A, which means A to C is also there. So does it include that too?
No. We check whether we got the original functional dependency or not.
That's
So
it, right, sir?
that is called the dependency preserving.
Okay. Okay, sir.
Okay. So okay. So for this one, so what?
But just a question. In the example that you did behind the back one,
Yes.
you will always get a subset, right? Because the way you have taken all the functional dependencies and all possible combinations for the two sub,
Yes.
so then it will always be a subset. So how will you know
Yeah.
whether
I will give an
lossless or
example. I will give an example in the BCNF when we discuss about the BCNF. Then I will show you how the dependency is a violated dependency preserve.
okay?
Yeah. So up to first NF, second NF, and third NFs, we preserve the dependence, this dependency preserving, right? But in the BCNF may or may not be, right? Preserve the dependency. Okay. Okay. So what is the normal form? So normal forms in each normal forms in the normalization, we define some condition in the that's normal form. So if in the first normal form we define some condition, if that condition is satisfied, then we can say this particular relation is in first normal form, and the second normal form is also some condition is there. If that satisfied, then we can say the second is also the third normal form. So that is normal form. So normal form means it is a condition in each level. So first, so what is the condition in the first normal form we see? Okay, just a minute. Hello. Okay. So what in the first normal forms? So this is in the first condition in the first normal forms. So a relation is the first normal form if and only the underlying domain contains the atomic value. Atomic value means that value is not divisible into further any components, right? So like if I give this example is like you can say name. So you already sees the in the this relational algebra, not relational algebra, year diagrams, right? Name is divided into first name, right? First name, middle names, and last name, right? So if it should not be like this one, so it should be atomic value, right? So what I exactly that means, let me define this. So it, so in the first normal form, all the attribute domains of the attribute should contain the atomic value only and does not have the multi-valued attribute. Okay. So in this particular example, student tables you can see. So student tables has the SID, SNAME and CNAME. So S1 is your atomic value. S name A is also atomic value, but in the C name you can see there is the two codes or subject C and the C++. So that is two value. You we put that in the C name also. So that is not atomic value. So this is a multi-valued attribute. So this is called the this C name contains the multi-value. Multiple value, and similar to this S2B and the C++ and DB also. So in the first normal form, this should not be there. So that's why it is given like this. And here also the given, your SID is the primary key, and here thus the MVA multiple value attribute is exists. That's why this particular attribute is not in first normal form. So to make these student tables into the first normal form, what you have to do, so whichever attribute is contains the multi-valued attributes, so that's value should returns in the next row. So in the next here you can see, so all the values should be right in the, each value is right on the next tuples, and you have to repeat this value, right? So here you can see C and the C++, and also similar this also. So now there is CNAME contains only this atomic value. So that's why it is now it is in the first normal form. But here now you can see whether now SID is your primary key or not. Here you can see in this table SID is your primary key, but in this table SID is not your primary key because the SID is repeated, right? But you knows that the primary key is a unique and not, right? So now what you have to do, you can split up, do like this. In the next tuple you have to write, and then you whatever attribute, so these two attributes, the primary key SID and the attribute you have done the simplified the value, so that's value together is your primary key now. Right. So here SID and the CNAME your primary key, right? So in this first normal form, now you can say this this table is your first normal form, right? Because all the value in the table says has the atomic value. Okay. But though it is in first normal form, then also the redundant is also present. So redundant means the duplicate value. So same value got repeated, right? So here you can see that problem is SID. As the SID S1 is repeated, A is also repeated, right? S2 is repeated, B is also repeated. So that is redundant, right? As we see in the previous example, update anomaly or delete anomaly may be occur due to this. So then we go for the second normal forms. So second normal form will resolve this one. Okay. Up to this is clear what is first normal form. Then we can move to the second normal form. So in the second normal form, there is two conditions that should satisfy. Then we can call that is as the table is in the second normal form. The first condition is R should be in the first normal form, and R should not contains the partial dependency. So what is partial dependency? Right. So let's see the definition. So let R be a relational schema. X, Y, and A be the attribute set over R, where X is any candidate key and Y is a proper subset of candidate key and A is non-prime attribute. Right. So we already discussed about what is prime attribute and what is non-prime attribute, right? So then Y to A is called the partial dependency. What this means? So suppose your candidate key is given. So suppose this is your 3 attribute A, B, C, and your functional dependency is given A, B to C, right? And B to C. This is your functional dependency. Here it is a clearly, we can say A, B is your candidate, right? But here what it has said, any proper subset, if any proper subset of candidate key, what are the proper subset of this candidate key possible? One is A and another is a B is possible, right? So but you can see in this B is a proper subset of the candidate key and derives the non-prime attribute, because the here prime attribute is your A and B, and non-prime is your C, right? So here you can see the proper subset of AB, that is B, and B derives the C. So this is called the partial dependency, right? I hope it is clear to everyone what is called the partial dependency.
So basically, sir, left-hand side should be the part of a candidate key and the right-hand side is not a part of the candidate key, then it is a
Yes,
partial dependency.
yeah, yeah,
So if
that
I
is
say
partial.
it in textual manner,
Yeah,
that should be the way, right, sir?
yeah, yeah.
So can you give an example with actual values? Like the previous one, we saw one table with some values.
Yeah, we will see in this example. So this is clear, right? What is partial dependency? This way. So that we will see how what is the
And sir,
problems.
also, sir, proper subset means do we take individual ones or it could be like suppose if I have A, B, C, D as a candidate key, and if I take A, B, C as one of the, is that also considered as
Suppose
a subset?
this is your candidate key. These are the value in the candidate key A, B,
Yeah,
C,
yes,
D.
sir.
Yeah. Other than this value, we calls the all the value we calls the subset, proper subset. Right? This
Okay.
is A, B, D. Other than that value. So many you know about the how we can create the
Yeah, yes, sir.
power set, except that value, and the null value also.
Okay. So suppose if I have ABC determines D, then that is not a partial dependency, but because all of them are part of the candidate key, right, sir?
A, B,
BC determines D.
D, right? So here you can see this is your candidate key then.
Yeah, and D is also a candidate key, right, sir?
No, how you D is okay. No, that is not a problem.
That is not a problem, right, sir? It will be a 2NF then.
The definition is this is a prime attribute. So definition is any proper subset of the candidate key derives non-prime attribute. But this is a prime attribute here.
Yeah.
So then that is not the partial dependency.
Okay, got it, sir.
This partial dependency, I'm still not clear.
Okay.
Can you explain a
So
little more on that?
okay. So
So we could take any one example from the activity questions. Probably there are many given there actually.
here you can see one example. Here the example is there.
Yeah, yes, sir.
Okay. So in this table, you can see SID is given to you. SID and CNAME is your primary key, right? So you can say the functional dependency is like SID, CNAME derives all other attribute that is CNAME. And also here you can see this one, SID also derives the CNAME. Not SID. Okay, just
No, your S name. S name is
yeah. S
given
name.
by SID and CNAME combination, right?
Yeah. Okay, so SID is derived your CNAME, right?
No,
No, not
no.
CNAME.
That's not. See, SID plus CNAME is primary key.
Okay, just a minute.
So your S name, if you want to arrive at the S name,
Yeah,
you have to
S
use a
name, S name.
combination of SID and CNAME.
No, but look at these tables. Every time S1, there is a value, right? S2, this one. So first I have write this one, SID to CNAME, SID to CNAME, that is S name. Yeah, sorry. Now I hope it is clear. So let me write here. So that is SID, right? CNAME. We can derive S name, right?
Correct. Yes.
And by look at this data, we can say also SID derive your S name. Now it is clear, right? there is two functional dependency. One is SID, comma CNAME derive SNAME and SID derive SNAME. Right here you can see SNAME. There are functional dependency can exist. You have to look this particular instance of the data. I'm deriving from this one. Right? And
Okay, we have to based on the data available to us or in general.
no, in general. So if you take any example, first you look some data, then you can derive functional dependency, then you put that constraint on the tables, right? So these are the constraint you want to apply in the tables. So this is one kind of constraint, right? This is you want to apply in your table, right? Constraint means a rule or conditions you want to apply. So here, how you got this one, SID and CNAME, right? So I doing the reverse engineering, you can say this thing. I just want to show you how this example arrives. Okay.
Okay.
So here you can see two functional dependency is present, SID to CNAME and SID to SNAME. So now, can you
Are we saying SNAME is partially dependent on SID?
yes. So here you can see what is your candidate key, SNAME. So this is your candidate key, right? SNAME. If you want to find how we finds the candidate key. So suppose this is your R has the SID, CNAME, right, and SNAME. So first we check the right hand side. Only right hand side, only SNAME is present. Then these two attributes should present in our candidate key. So that's why we try to find the closer set of that, right? So that is the close. If we try to find the closer set of that, so that is your SID, CNAME, and SNAME. So that is equal to R, right? So this is your candidate key, right? So candidate key is your SID and CNAME. But here you can see this is satisfy the condition because this is not the proper subset of candidate key and derives the non-prime attribute. Then this functional dependency in the second normal form, right? But if you check this one, you have to check whether this is a candidate key. No. Whether it is a proper set of a candidate key or not. Yes, it is a proper subset of the candidate key. SID is a proper subset of whether it derives the prime attribute or the non-prime attribute. So it derives the non-prime attribute, right? So then you can say this particular functional dependency contains the transitive dependency, right? So the whole R is then you can say this is not in the second normal form.
So even the first functional dependency is not is partially dependent, right? Because it is SNAME that is on the right hand side.
This first one, no,
Yeah,
this
first
is
one.
whether this is a proper subset of a candidate key.
It is, yes, sir.
No, it is not a proper subset. Proper
It is the
subset.
entire set, right, sir? So that
Yeah,
isn't a
yeah.
subset. Okay.
No. I'm talking
Okay.
about the
Okay. So
proper
it has to
subset.
be a
Proper.
subset. Okay.
Yeah,
Okay. Fine, sir.
proper subset. Okay.
And sir,
So,
if there are multiple, suppose like here also there are two, if there are some 4, 5 functional dependencies that have been given, we have to check for each and every one of them, right?
no, yes. I have checked this one is the satisfying the second normal form condition. That's why
Yeah.
checks the next one, right? So it got violated the second NF condition. Then I no need to check further. I can say this particular relation is not in the second normal form.
So every functional dependency has to follow that rule. Only then would it be in second normal form.
Yes, yes.
Okay.
Then
okay,
you
sir.
can say that. Yes. Okay. So this is called the transitive dependency, and this violates the second normal form, right? Not in second normal form. So for that we have to make it in the second normal forms. So how we can make it? So let's take this example. So here you can see this box is given. So SID and PID together can determine quality. So let me write SID, PID together determines the quantity, and only SID determines CT, and SID determine status, and CT determine status. So can anyone tell me what is the candidate key here? So you know how to find it, the
It will
candidate key.
be SID status city is one key, right?
Yes, let me check. You have to check the right hand side. So that is quantity is present.
No, I was
City
just
is
going based on the data available. There'll be
yes,
one
yes.
table which is SID status city and another table which has SID, PID, and quantity.
No, no. Only consider the whole table as these are the. Consider this is a supplier tables relations, is supplier relation, and this is your functional dependency associated with it. Now you have to find the candidate.
So if you look at all the right hand side, quantity, city, and status, they're covered, right? 3 out of 5 are covered. So whatever is left, which is SID and
PID.
PID, they will be the candidate key.
Yeah, exactly. So these are the candidate key, SID, hence the PID, right? Now you have to check the condition whether it is in the second normal form or not. Okay. So we have to check the first condition. Here you can, this is whether this is a proper subset of candidate key. No. So it is itself the candidate key determines the non-prime attribute. Then this is in the second normal form. Second one, this is a proper subset of candidate key. Yes. And it determines the non-prime attribute, right? So it is not in the second normal form. So we have to, so decomposition is a technique in which we can make it into the second normal form. So this particular functional dependency violates that condition, right? So you have to make this thing, we need to decompose the tables, right? So for that you have to check whichever particular functional dependency violates the condition. So here you can see SID to CTs violates the condition. Then you have to finds the closer set of that. So this left hand side. So here you can see SID, right? So what are the closer set of value? That is SID, CT, and the status, right? Then you have to create, you got these are the attribute, right? Then you have to decompose a relation R. Suppose this is your R. So that is decomposed into one table. So that contains all these attribute, right? SID, okay, SID, CT, and the status, right? And you have to write also associate all the associated functional dependency also along with it. So suppose the F1 has the functional dependency that is SID, right? Okay, let me write in the clear sheet. Okay. So you decomposed R into R1. R1 has SID, CT, and the status, and the relate associated functional dependency are SID to CT, CT to status, and SID to CT. Any other functional dependency possible? No, that is not possible, right? So this is clear, right? So now you have to understand this. Right. Now you have to create one tables, right, that contains all other attribute except this attribute, except this attribute. So that is your R2, that is SID and PID and quantity, right? So this is one relation, and this associate functional dependency are SID, PID to quantity, right? So F2 contain SID, PID to quantity, right? We decomposed the relation R into two relation R1 and R2 because it violated the second NF condition. So that's why we decomposed into two relation. Now you have to check again in this particular decomposition whether it satisfies the second NF condition or not. If it satisfies the second NF condition, then keep at it is. Otherwise, you need to further decompose it. Clear? Hello. Up to this is clear, right? R1 and R2 and the functional dependency. Now you have to check again. You have to find in this, consider this as your original relation, and then you have to find the candidate key again. So in this candidate key is this is only one functional dependency. So you can say this is your candidate key, and candidate key determines the non-prime attribute. So this is in the second normal form, right? So no need to, but in this R1, you have to again find the candidate key, right? So here you have to check whether status and the city is present in the right hand side. Then you can say you have to find the closure set of SID. So that is your SID, city, and status, right? So that is equal to R. So your SID is the candidate key. So now you have to check one by one whether it satisfy the second NF condition or not. So SID is a proper subset of candidate key. No, because it itself is a candidate key and it determines the non-prime attribute. Again, CT is your proper subset of candidate key. No, and it determines non-prime attribute. So this is not a transitive dependency, right? Hello, any confusion here? And in the third one is if SID itself is a candidate key and determines the non-prime attribute. So now we can say this is in the second normal forms. R1 and R2 is in the second normal, right? Okay. Now second NF is clear. Now we will see the third normal form, right? So in the second NF, we see there is two conditions need to be satisfied. The first one is it should be in first normal form, and it should not contain any transitive dependence. Similar in the third normal forms, R should be in the second normal form, and R should not contain the transitive dependency. So transitive dependency is simply means like this: A to B and B to C, right? If this kind of functional dependency, so here you can clearly say A is your candidate key, right? A is your candidate key, then prime attribute your A, and non-prime attribute is B and C. So what is the definition of the transitive dependency? Non-prime attribute should not derive any non-prime attribute. Okay, transitive dependency. Non-prime attribute should not derive. Should not derive the non-prime attribute. No, transitive dependency means if non-prime attribute derives non-prime attribute, that is called the transitive dependency, and this should not allow in third normal form, right? So the exactly same thing is written here also. So this is one condition, or you can say the same thing in another language. So that is your, when we calls the relation is in the third normal form. If it is in second normal form, if R is in second normal form, or R is in the functional dependency is trivial. Do you know what is trivial functional dependency? Anyone?
Sir, it's like AB determines A.
Yes, that is AB determines A. If this kind of transitive functional dependency it has, then we calls this is in the third normal forms. No need to check other condition, right? So this is already in the third normal form. The second condition is your X is a super key of, so this is if alpha to beta, right? This is in a functional dependency alpha to beta. So this is your left hand side and this is your right hand side, right? So if left hand side is your super key or beta side is your prime attribute, So this is exactly that. So this is whether if some functional dependency is, if A is your super key or beta is a prime attribute, then you can say that is in the third normal forms, right? So we will see what is the problem in the second normal form. So that's why we go for the third normal form. Okay, so here one thing you can see. So this is your tables, right? After decomposition, we decompose the tables into R1. So this is your R1, right? This is your R1, SID, status, and the city, right? So hence the functional dependency is given here. So that is R1 functional dependencies, SID to city, SID to status, and city to status. Now, okay, so let me tell you what is the problems in the first here. So, okay, SID to status and city to status, right? So every time here you can see, every time we repeat this city daily, this status got repeated, right? Every time we, so this is one kind of redundant, right? So in the third normal forms, we remove that redundancy also. So it has the, this is in the second normal forms, but not in the third normal forms, right? So that's why how to decompose that things and into the third normal forms, and whether you have to check whether this relation R1 is third normal form or not, right? So it is already in the second normal form, so we need to check whether this particular functional dependency is in third normal form or not. So for that, you first you have to find the candidate key, right? So here candidate key we already find, so that is your SID. So now you have to check one by one functional dependency. First functional dependency, whether this is a super key. Yes, it is a super key, so no need to check for this condition. So here it is given, you have to check whether this is in the trivial functional dependency, or left hand side is your super key, or right hand side is prime attribute or not. If any of these conditions satisfy, then you can say that functional dependency is the third normal. So this is your candidate key, or then it is also a super key, right? So SID is your super key, so this is in the third normal form. Then you have to check for this one, SID. Again, this is the satisfy the this second condition. The left hand side is your super key, right? So this is also in the third normal form. Now you have to check for this one, whether this is a super key. Left hand side, city is a super key. No, this is not a super key. Now you have to check the third condition. That is your, whether the right hand side is a prime attribute. Status is your prime attribute, not. It is a non-prime attribute, right? So this is violates your third normal form condition. So overall, the relation R1 is not in your third normal form. So now how to decompose this functional dependency into the third normal form, to make it third normal form. So for that, you have to check which functional dependency violates the third condition, means third normal form condition. So this is violates the third normal form condition, right? So for that you have to find the closure set of that. So you have to find the closure set of that. So that is city and status, right? So for that you have to create a tables, separate tables. So you already in the R1. So for that you have to create one separate tables, that is you can say R13, right? R13 contains this information city and status, right? So city and status, and you have to write also the associate functional dependency with it. So that are SID to status, not because this sorry. So that is your city to status, right? Any other functional dependency possible? No. Okay. Now you have to write. So the for writing the second tables, so the formula is, suppose the alpha to beta violates the condition, third normal form condition. So you have to make a tables. You have to find the closure set of this one, and you have to create the tables. Then you have to write whichever uh, tables. So that is R minus beta. The next table will contains the all the information, that is R minus beta. So in R14 you can see R14 will have the SID and the city, right? Beta is already the status, right? It has your status, so no need to write here in the R14. So then you have to write the functional dependency associated with R14, that is your SID to city, right? So this is the way to decompose into the third normal form. Now you can check the whether this decomposition is in the third normal form or not. So here you can see in this functional dependency, city is your candidate key, and candidate key determines the non-prime attribute. Similar for this one, SID determines. So now this is in the third normal. So hope this is clear up to third normal form. Now we will see the BCNF, right? So in the BCNF, you can see the third normal form. There is in the third normal form, the condition is there is three conditions, right? First one is the functional dependency is a trivial functional dependency or not, or left hand side is a super key or not, and the third condition is right hand side is prime attribute or not, right? So these are or condition, at least one of these condition. If at least one of this condition is satisfied, then you can say this is in the third normal form. But in the BCNF, there is a restriction, or it is BCNF is said the more restrict form of the third normal form. That is, we consider only the left hand side should be the super key, right? We not see these conditions that is on the right hand side. So in the BCNF condition, this condition need to be satisfied. Right? Only there is one condition, that is left hand side should be a super key, right? So
So here also it is or it is and the two conditions.
this is OR.
Or is it okay?
Yeah, we can consider if the trivial functional dependency, if it is the trivial functional depend, then you can say directly that is in BCNF.
Okay, sir.
Okay, so here you can see this particular functional dependency. So this table has this functional dependency, right? So you have to find the candidate key here. So can anyone tell what is the candidate key here? So this
Student
is
course here.
okay. So student course. Right, this is one candidate key. And another candidate key is also possible. Student course, student instructor. The closest set of student. Okay, not possible. So only one candidate key is there. Okay. So this is the candidate key, student and course, right? Now you can see prime attribute is your student course, right? And the non-prime attribute is your instructor, right? Right? Okay. So now you have to check the BCNF condition, whether it is in the BCNF or not, right? So for that, you have to first check whether this is one functional dependency, this one is the second functional dependency, right? So you have to check whether right hand side is your primary super key or not. The student course is a candidate key, so it is super key, right? So right hand it satisfies the BCNF condition, right? But here you can see whether instructor is a super key. No, it is not a super key. Then you can say this is not in BCNF, right? So now you have to make the decomposition to make it the BCNF. So what is the rule? So suppose this x to a violates the condition of the BCNF, right? This function, if this functional dependency is violates the condition of the functional dependency, then you have to decompose the R is such that R1 contains the attribute of RA, right? And the second table is contain the R minus A attribute, right? and then you can write the associate functional dependency, that is associate with it. So RA1, so here you have to write the R1 is your instructor, right, and the course, right. F1 is a course and instructor and course, and R2 will contains the attributes, that is your A. A is your course. Except course, all the attributes should be there. So that is your student, right, and instructor, right. Now you have to write the functional dependency associate with it. Okay, so that is your here F1 should contains the functional dependency, that is instructor to courses, right. And what is the possible functional dependency in R2? Any functional dependency possible? No, there is not possible. So this is an example where we lost the this functional dependency. We not preserving this one, right? So you cannot reconstruct it from this decomposition to the original functional dependency. So that's why we said that the in BCNF not guaranteed that's the it's depend preserve the functional dependency. Okay. Any other doubt? Hello. So that's it for today's session. You have any doubt? Means the normalization you can ask. Am I loud and clear?
Yes, sir, you're audible, sir. Thank you, sir. Thank you for the session.
Yeah. Thank you, everyone.